All right, ladies and gentlemen, this class recording has started. So, today, to wrap up our unit on forces and Newton's laws, we'll take a look at this problem set called forces on inclined plane. Like I mentioned to you earlier at the beginning when we were going over the schedule, we're really going to put together about 3 topics today. 1, we're going to deal with components. 2, we're going to deal with equilibrium. And then 3, eventually, we're going to deal with friction. So let's start off, though, with just components and equilibrium. And let's take a look here at problem number 1. Okay? So let me go here and here. Okay. Yes, this will be the last part of your test. So. Alright, so it says, a car rests on a slanted ramp leading onto a car transport trailer. The car's brakes and transmission are released, so only a cable attached to the car prevents it from rolling backwards off of the ramp. The car has a mass of 1,000 kilograms, and the ramp is inclined at an angle of 15 degrees, which is represented by this letter alpha here in the picture. This book chose to use alpha. That's a lowercase alpha. It just represents the angle. Right? So it says, find the tension in the cable, normal force from the ramp acting on the car. I'm actually going to do this real fast because I'm going to need 2 of these. All right. Okay. Let's start off here with letter A. And our first step in the process, right, is to do what? What we're looking for. So what are we looking for in A? Tension, right? So our tension force is our unknown. Okay? After, oh, by the way, the back of this page is totally blank, so if you want to do it there or if you want to do it in the space next to it, totally up to you, but you have some space there to work on it. So, all right. What we're looking for, what's next? What we know, right? So we go through, they gave us that the mass is 1,000 kilograms. Actually, it's only 1,000 period, but oh my goodness, whatever. Okay? And then they also gave us that the angle alpha in this picture is 15 degrees. Okay? When I freehand write my alpha, it looks kind of like a little fish. Yeah, so. All right. There is one other piece of information here that, even though it doesn't specifically say it in the problem, is going to be really important for us figuring out what's going on. What's the other thing that it tells us about this situation? Well, we can figure that out. We can figure out the weight. It doesn't specifically tell us in this problem. But there is one other piece of information that's kind of important. Devin, the car is motionless, right? The car is motionless. And Devin, motionless is an example or an application of what? Equilibrium. And so that means that we know, even though it doesn't specifically tell us in the problem, that net force has to be 0 in this problem. Okay? Good there. Okay. What we're looking for, what we know, because this is a forces problem, now we go free body diagram. Okay? Here's a picture of our car. I am going to draw a dot right in the middle of the car to represent the middle of that car. Okay? And we'll draw all of our forces from there. So, what? First force we can put on this drawing is what? The weight, right? What? Weight comes from where? Well, weight, by definition, is the what? Force of gravity, right? And gravity pulls things which way? Straight down, okay? That's going to be important to this problem, all right? So that's here, right? Here's our weight. Fuad, you told us that we calculate the weight by doing what? M times G, right? And because our weight is 100 newtons, we can do that pretty quick, okay? All right, good there? Okay, next force we want to put on this drawing. What's next? Normal force. Okay, Yusuf, normal force is going to be here, right? That's actually part B of this problem, but it's going to be important for our free body diagram. Do we remember back from the very, very beginning how we define normal force? And if you don't use it, we can like go somewhere else. So, somebody else? Anybody? How do we? What makes it a normal force? Ah, not true. What does it do? No. 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 Okay. Here's our definition of normal force. Normal force is a force that is perpendicular to the surface that causes it. No, you didn't. Okay. Normal force will cancel out gravity, or can cancel out gravity, if we're dealing with a horizontal surface. Because perpendicular to a horizontal surface is straight up. But remember, right, I gave you this situation, too, right? Which way was normal force in this situation? The wall, so that means that it's actually along the x-axis in this problem, right? Okay, or in this situation. There was a problem that I gave you guys that you were supposed to work on. I think it was friction, one of the additional friction problems, where I gave you a problem where it was on the ceiling, right? Where it was there was a object that was being pushed along the ceiling. In that case, normal force is actually downward because it's perpendicular to whatever surface that is causing it. Okay? Does that make sense? Now, that being the case, right? So, Yusuf, what's causing the normal force in this problem? The slant, like the ramp that it's on, right? But the ramp is not horizontal. It's tilted at a 15-degree angle. So that means there is a normal force in this problem, but it's going to go like this. Does that make sense? Okay? Now, almost every other problem that we've done, what have we just assumed about normal force? Well, we did assume that because those were all the problems we've done. What about the value of normal force? It's almost always the same as gravity. Can that be the case in this problem? No. Forces that don't point exactly opposite of each other can't cancel each other out. All right? So we can't make that assumption in this problem. All right? It's another force that's on our drawing, but we can't make the assumption that it's exactly the same as gravity. Okay? All right. Third force that's acting on our car. The pulley or the string that's attached to it, right? Or the cable. Okay? What do we call forces that come from cables? Tension, right? So the red force, that's our unknown in this problem. That's what we're trying to figure out. Okay? Good there. In the end, what do we know has to be true about all these forces? They have to equal zero, or they have to do what? They have to cancel each other out. Okay? All right. We have forces that are at angles here, either not straight up and down, not side to side. What have we done with all the forces that we've encountered like that in the past? Make triangle, right? What do we call that triangle? We find the... What do we call those missing sides of the triangle? Which vectors? The component vectors, right? You knew what you had to do. You just weren't calling it the right name. That's okay. That's why I'm giving it to you like this, right? All right. So we start off then, and I'm going to make myself. So I don't want that.
Oh, I like that color.
Yeah, it's kind of hard to see. That's the problem there. All right. So we'll go here and give ourselves an x-axis, and here give ourselves a y-axis. I'm going to move this over a little bit. Okay. Let's see if this works. Hope it does. Ugh. I was going to do this before school too, and I forgot, so... No. Forgot which button it was. And there we go. Okay. So here, I'm going to do this. All right. And I'm going to slide this up and put it right there in our drawing. Okay? Now, wait, before you draw that, there's a reason why I did it. Okay? All right. There's our x-axis, there's our y-axis. We split up forces into components if they are not on the x-axis or the y-axis, correct? Okay? Because then they have a horizontal and a vertical. So in this case, right, we would split up normal force and tension. Because neither one of them is on the x-axis, right? But, Cindy, mechanically, how do we find the normal, or how do we find the components of a force? SOHCAHTOA, right? But generally that requires that we know what about that triangle? One angle and one side, right? If you're going to use SOHCAHTOA, you got to know one angle and one side to find the other, okay? So we could probably figure out some angles here because we know this one. We can do some trickery and figure out what the angles are. But do we know the normal force in this problem? We said it's not equal to gravity in this case because it's not right opposite of gravity. Do we know the tension in this problem? We don't, right? James, go ahead. Good. Yes. So James asked, would the vertical components of tension and normal force equal the weight? And the correct answer to that is yes. And tell me something else. There's one other thing that we could kind of make a jump from there, James.
Oh, I got you.
The horizontal components of normal force and the horizontal components of tension would have to cancel. All right? Because we got to make everything add up to what? 0. But again, do we know enough information to find those horizontal and vertical components? It's going to be kind of tough, all right? So here's what we do in this case, all right? This is not intuitive in any way, but this is the easier way to handle it. We really only know one force in this problem, right? We know the weight force, okay? So we've never split up weight into components before because it's always on the y-axis. But that's just because that's how we draw the x and y axis, right? We draw it conventionally, horizontally, and vertically because that's how we've always drawn it in math class or whatever. But remember, from way back like the second day of class, we can choose any frame of reference or any coordinate system that we want, right? We don't have to do it conventionally as long as it makes sense to us and serves our purpose. We can choose any coordinate system we want. Okay? Does that make sense? So here's what I'm going to do. I'm going to take my x and y axis, and I'm going to tilt it, maybe, 15 degrees. Like that. I'm pretty impressed with myself, actually. That's pretty good. That's always the key when I'm doing this is do I draw the forces? I'm a little bit off, but okay. All right. So I'm a little bit off, but by tilting it 15 degrees, now my normal force is on my y-axis, even though it doesn't quite look like it in the problem. It's supposed to be, all right? Now my tension force is on my x-axis, okay? And that means that the y-axis is perpendicular to the surface, and the x-axis is parallel to the surface. Okay? That good? But the ideas of equilibrium still have to hold true. We still have to have equilibrium on the x-axis and the y-axis. Okay? But by tilting our frame of reference, what about weight now? Is it on an axis? No. And what do we do with forces that aren't on an axis?
Split. Oh, now you can split.
We break them up into what?
Component vectors.
We break them up into component vectors, all right? Component vectors always run along the axes of the problem. They're horizontal and they're vertical, even though now horizontal and vertical aren't exactly straight up or side to side. Does that make sense? We okay with that? Okay? So, gravity has two components now. It has a component that runs this way, even though my pen is deciding it may or may not draw it. And it has a component that runs this way. Does that make sense? Let me pull it out of the drawing here real quick. Gravity is still straight downward. Okay? But now, this component runs this way. And this component runs this way. That's not to scale, by the way. I just draw it kind of like that. Okay? What do we know about the two components? If one's horizontal and one's vertical, what has to be the angle between them? 90 degrees. So there's a right triangle. What about the hypotenuse of this triangle? Do we know the hypotenuse of that triangle? It's what? It's the weight, right? Which we've already calculated is 9,810. But we said to know, or to use SOHCAHTOA, we have to know a side and an angle other than the 90 degrees. Okay? We tilted this XY axis 15 degrees to match the ramp that's in the problem. And that means that the y-axis used to be right along the green arrow, but now it's 15 degrees tilted. So this angle right here is 15 degrees. Good? Now do we have enough information to find the two sides of that triangle? We do. We can use SOHCAHTOA. Even though it's not oriented the way a right triangle usually is, it is a right triangle. Austin, go ahead. You could flip the triangle and make it go this way and this way.
Yeah.
Okay? We could do that. Then, the reason that we usually do it this way, Austin, is that now this 15-degree angle always matches the angle that the ramp makes with the ground. Okay? I can show you if you want to. I can show you, it adds up to 90, or you can just trust me, all right? You could do it this way, but then this angle, by tilting or making the triangle this way, that 15 degrees is already in the triangle and we can use it right away.
Yeah.
If we drew the triangle the other way, we could still do that. We would just have to do a little subtraction. This angle would be 75 and we could go from there. But yes, you could.
Yeah.
It doesn't matter which way you make the triangle, as long as you get the angles right, you're good. Good. All right, so go. Figure out the two sides of this triangle, right? I'm waiting because I don't want to plug stuff into my calculator. It's Monday morning. Like, man. So, did you do it already? Okay. What's this one? Yeah, it should be the long side. Even though it's not like that in the picture, that should be the long side. All right. Does that make sense? Okay. Even though my triangle is not drawn to scale, if this angle is 15 degrees, right, this side of the triangle is going to be relatively small, and this side of the triangle is going to be relatively big. Yes? Okay? All right. Name-wise, we refer to this as the weight. Okay? That means here we a lot of times refer to this as the perpendicular component of weight, because it's perpendicular to the surface that it's sitting on. And a lot of times we'll refer to this as the parallel component of weight, because it's parallel to the surface that it's sitting on. Okay? Does that make sense? All right? James. What's going on with my color here? I don't like that at all. But did it just get like yellowy? Like what, sepia? Like, yeah, so. All right, James, let's now use some of the intuition that you had before, right? Can we figure out what the normal force should be now in this problem? Well, actually, let's do tension, because that's what this problem actually was originally asking us for, right? What does the tension have to be equal to in this problem? The parallel component of weight. Why? Because what has to be true on the x-axis? They have to be equal to give us equilibrium, right? So the tension force here has to be equal to the parallel component of weight, because we got to have equilibrium on the x-axis. All right? And then for part B, what does the normal force have to be equal to? The perpendicular component of weight, because on the y-axis, what has to be true? We got to give us 0, right? So that the normal force then would be equal to 9,475. God. Does that make sense? We have introduced no new concepts in this problem, right? We've applied them differently, but we've introduced nothing new. Normal force, perpendicular to the surface that causes it. Equilibrium, net force equals 0. Equilibrium in 2 dimensions. Net force x, net force y have to equal 0, right? Component vectors, right? As long as we know a side and an angle, we do one along the x-axis, one along the y-axis. We've never split gravity up into components before, but we're just applying things that we've done already to a new situation. Austin, go ahead.
So basically, so you find attention by using the y-axis value, right?
I guess we'd probably go x. We'd probably call this one the x-axis.
Or axis.
Yeah.
You don't know, I'm just
Yeah, but yeah, I just want to make sure we're clear. But yeah, we found tension because now, Austin, right? If we get rid, when we do things as components, right? Basically, what we're doing is, let's see if this works. It's not going to work. We're basically getting rid of this force and replacing it with those two components, right? A trip to the northeast is a trip to the north and a trip to the east, right? You'll end up in the same place if you go northeast or if you separately go north first and then east second. Does that make sense? So splitting something into components is essentially removing the solid force and replacing it with the dotted components. Does that make sense? Yeah. Now, if we look at our free body diagram, how many forces do we have on our x-axis? 2. One of them's tension. This one, even though it's not on the x-axis, is still an x-axis force, right? Yeah. Not drawn to scale, but if it's not moving on the x-axis, what has to be true about those forces? They have to cancel, right?
Oh, so it's 2539 if it's
Yep. Yep. And then same thing on the y-axis, right? Yeah. That there's 2 forces on the y-axis. This perpendicular component, I just moved that triangle out here to give us a little bit more space to write, but it's the same triangle. So yeah, the perpendicular component of the weight plus the normal force have to equal 0. Okay? Good there? Technically, if we were to write, so Cindy asked about the positives and the negatives, right? Okay, and I don't remember or not, Fuad asked about that the other day, and I said, when we're doing pictures, let's just leave the numbers, because the arrows will tell us the direction. Technically, if we wanted to do this, we would know that the net force on the x-axis has to equal 0, right? And then right?
Yeah. Oh.
here we would have to make one of these positive and one of these negative to get us to 0. But when we're just like figuring this out, let's just arrows, right? We know those two have to be equal. Go from there. Okay. Devin, go ahead. That is gravity in this case. Okay. But nice transition, Devin. Let's take a look then at question number 4. Question number 4, is that what I want? 3. That's okay. We'll draw a picture. Yes, Hannah, go ahead. Good. If I gave you a question like this on the test, Hannah, this would probably be like 2 separate parts. You know, like I'd give you some points for the first one and some points for the second one, right? But here, yeah, you're kind of doing the same thing, right? It's just, are you doing the x-axis, you're doing the y-axis, basically, so. Okay. But I would say probably there's a better chance you're going to have both parts on the test, but they would be split up into 2 separate sections on the test. Find this, then find this. Okay? Austin, go ahead. I don't usually put bonus questions on the test, so yeah. So. I make the test, but I have looked at some old IB tests and some sample tests and things like that. Some of them you might be able to find, although the ones I have are on the coded site that you need like passwords and stuff to get on. Unlucky. All right. Question number 3 says a 91 kilogram refrigerator is sliding down a ramp inclined by 27 degrees at a constant speed. What is the coefficient of kinetic friction between the ramp and the refrigerator? And remember, this is an old problem, so it's kinetic friction. That's the same as dynamic friction. We go from there, okay? All right, so let's go through the process, right? But we talked about that in order to figure out the coefficient of friction, we need to know 2 things, right? What do we need to know? Do we remember?
The net force?
Not the net force. The normal force.
Oh, I know this is N.
And that's the static friction. But
It's self-help.
we need to know what is the force of dynamic friction, right? Remember, there's a difference between coefficient and force, right? We need to know the force of dynamic friction and the normal force. Did you find it, Cindy?
No.
Oh, I didn't know if you were looking for it or not. So. And that's the formula that we use that puts it all together, all right? Okay? Good there?
This is topic 2.
No, it's chapter 3.
Oh.
The section of friction. Oh, no, sorry, it's chapter 2. It's section 2.2.
I feel like in R.
No. Here, over here.
Yeah.
R.
Let me see. Yeah, what's that R?
R.
Here, right? Here, right?
R?
R.
Let me see.
R. You R.
That's N. That's normal force. I'm not sure why that R is there. That R should be N or F of N. So everybody know what everybody understand. Here, because it's a recording, I'll show you real quick. All right, here.
Oh God, if I didn't like think on this.
Yeah, I know.
What are you talking
Okay, so in your physics data booklet, okay, if you go to page 5, that's where the equations start. So we're in subtopic 2.2. Oh. And it has F equals ma, so that's Newton's second law, right? Okay. Then it has the two formulas for your coefficients of friction. S is static, D is dynamic. And then it has this R over here on the side. Not sure where R is coming from, right? That R represents normal force. All right, so if you want to adjust that in your book, keep that in mind. That's normal force right there.
Is that just the ID way that?
I don't even know, because in your book, in this book, you know, your paperback, it doesn't have R. It has N. Maybe, but make sure you understand the concept of it more than the actual writing of it and stuff like that. So. Remember that when we're dealing with the static, that's like we're dealing more with the maximum friction. So when you get to the maximum, they're equal. Yeah. Yeah. Coefficient does not have a unit, right? Because it's force divided by force, basically. So. All right, Joe, go ahead. Do they have R in there? Crud, my bad. I'm not sure why R is on there. I would much rather call it N, but you know. So. It says it is R in your book, so sorry about that. Yeah, really normal. It's like really normal. So. All right, let's do this. Okay. Oh man.
Let's do a smiley face.
A smiley face doesn't really represent a ramp, so I'm not gonna do a smiley face. All right. Actually, let me do this. Good. Alright, so this time I'll draw the ramp slanting the other way so you see that it works, because if I draw the ramp the same way every time and then I give you a picture on the test that's opposite, then you'll be like, what's going on? So, alright, so there is our ramp, and then here is our refrigerator. There we go. Yeah, like I mean, if it was a square refrigerator, I like it like one of those small refrigerators that you can get like for a dorm room, kind of squarish. So, all right. So forces. First force. We have our weight force this way, right? We calculate the weight, m times g. They gave us a mass, so we can figure out what the weight is, right? Anybody do that real quick? No, my calculator. What is it? Okay, 892.71. Okay. There is a normal force in this problem, but like we just talked about, normal force is not opposite of gravity in this case, right? It's perpendicular to the surface. It goes like this, okay? It tells us that this refrigerator is sliding down the ramp at a constant speed. There's no tension force on this box or on this refrigerator now, but there is an opposition force, right? If it's sliding down the ramp to the right, what else is acting on it? Friction. Friction always acts opposite of stuff, right? So in this case, which way is friction acting on it? Left, right? Or up the ramp, right? Okay? And because it's sliding, that's going to be dynamic friction. Okay? Good there? Okay. Like we did before, there's an x-axis, there's a y-axis, okay? bring that up here. But same problem, right? Two forces, not on the x-axis, not on the y-axis. We have to split up into components, but we don't know either one of them. So that makes it easier if we rotate wow, my normal force is bad this one. Right? Just like that. Right? And we said that we always rotate an angle that is equal to how much the tilt of this ramp is. Alright? So if this is 27 degrees here, that means this angle right here is 27 degrees as well. I know it doesn't look it in the picture, but I just winged it. So. Good there? Alright, bell's about to ring. All of the answers to those problems that are on that sheet are posted on the calendar for today's date. All right, it says homework, finish up angle friction problems. They are all on the calendar. Devin, go ahead. The one on the left this time. It's always the angle between the gravity force and the new y-axis, because that's how much we tilt the xy axis. Devin, does that make sense? Okay, so this angle here, and this angle here are always going to be the same. Okay? All right, I'll see you guys tomorrow. We'll review some stuff, bring questions. Don't forget to watch that Newton's third law video that I posted. It's pretty awesome.